In this class, we discuss binary operations in abstract spaces. Okay. Consider a non-empty set X. A function or an operation star defined on X is called a binary operation if for any pair of elements A and B in X, the image of A and B under the operation star, that is A star B, A and B are operated by star, is also an element of X. Then star is said to be a binary operation. That is, for every pair of elements A, B in X, A star B is also an element of X. Then star is called a binary operation in X. Okay. If star is a binary operation in X, X is said to be closed with respect to star. X is said to be closed with respect to the operation star. That is, X is closed with respect to star if for every A and B belongs to X, A star B belongs to X. For example, consider the set R of real numbers. For any two real numbers R1 and R2, we define the usual addition as the operation R1 plus R2. Then R1 plus R2 is also a real number. That is, if R1 and R2 belongs to R, then R1 plus R2 also belongs to R. Therefore, addition of real numbers is a binary operation on the set of real numbers. Similarly, if subtraction is also a binary operation on the set of real numbers. Since R1 and R2 are real numbers, R1 minus R2 is also a real number. But if we consider the set 0, 1, 2, 3, etc., the set of non-negative integers, here also addition is a binary operation because for any two non-zero integers, the sum is also a non-zero integer. But the subtraction is not a binary operation. That is, if 1 and 2, for example, 1 and 2 are non-negative integers, but their difference 1 minus 2 equal to minus 1 is not a non-negative integer. That is, 1 minus 2 not belongs to the given set. If the set is n, then n is not closed with respect to subtraction, but n is closed with respect to addition. So addition is a binary operation on the set n, and subtraction is not a binary operation on the set n. For this binary operation, we can define certain properties. First is commutative property. Okay. If A and B are any two elements of X and A star B is same as B star A, then the star is said to be a commutative operation. For example, addition is a commutative operation on the set of real numbers because R1 plus R2 is same as R2 plus R1. But subtraction is not commutative in the set of real numbers because R1 minus R2 not equal to R2 minus R1. Okay. So the operation star is said to be commutative if for any two elements A and B, A star B is also A star B equal to B star A. We define associativity. Associative property. Okay. It shows that for any three elements A, B, C, A star of B star C same as A star B star C. We can show that subtraction is not associative, but addition is associative in the set of real numbers. This is associative property. Next one, the existence of an identity element. Identity element. Okay. The property is that if there exists an element E with A star E equal to A for all A belongs to the set X. A star E equal to A for every A belongs to X, then E is said to be the identity element of the set X. Okay. For example, if we consider the set of real numbers and addition as the binary operation, then 0 is the additive identity. 0 is the identity with respect to addition, that is additive identity, because A plus 0 equal to A for every A real number R. Okay. Now, if we consider the space R2, R2 means it is R cross R. It is the set of all ordered pairs of real numbers x1, x2 such that x1, x2 belongs to R. This is R2, the set of all ordered pairs. Here the additive identity is the ordered pair 0, 0. So additive identity of R2 is 0, 0. Similarly, we define R3 as the space R cross R. It is the set of all triples x1, x2, x3 where x1, x2, x3 are real numbers. Here the additive identity is the triplet 0, 0, 0. Similarly, we define the space Rn. Rn is R cross, etc. n times. So, it is the set of all n tuples of the form x1, x2, x3, etc. xn, where xi belongs to R for every I. Here, the additive identity is 0, 0, 0, etc. The n tuple of zeros is the additive identity. And in any space, the additive identity is denoted by the symbol 0. In R, it is the digit 0. In R2, it is the ordered pair 0, 0. R3, it is the triplet 0, 0, 0. And in Rn, 0 means 0, 0, 0, 0, etc. to 0 as an n tuple. Okay. This is the existence of identity. Similarly, we can define the inverse of an element. Inverse. Corresponding to an element A, if there exists an element B such that A star B equal to the identity element, then B is said to be the inverse of A. Also, A is said to be the inverse of B, and we write A equal to B inverse or B equal to A inverse. B is the inverse of A if A star B equal to B. And A is similar, if B is the inverse of A, then A will be the inverse of B. And symbolically we write A is B inverse equal to A, or A inverse equal to B. Okay. For example, in the set of real numbers, if A is any real number, its additive identity is minus A. In R2, the additive identity of an ordered pair x1, x2 is minus x1 minus x2. In R3, additive identity is x1, x2, x3. Its inverse is minus x1 minus x2 minus x3. Similarly, in Rn, the additive inverse of any element x1, x2, x3, etc. xn is minus x1 minus x2 minus x3, etc. minus xn as an n tuple. This is the case of additive identity in the space R1, R2, R3, etc. Rn. Okay. Now, we consider a set F. F is a field, and in the case of linear algebra, F is either the set of real numbers or it is the set of complex numbers. In linear algebra, a field represents either a set of real numbers or a set of complex numbers. If R is the set of real numbers, then F is said to be a real field. If F equal to C, it is called a complex field. Okay, and we define F2 as F cross F, F3 as F cross F, etc. Fn as f cross, f cross, f cross, etc. n times. Okay. For a set F, we define F2, F3, etc. Fn as. So F square means is this a set of all ordered pairs x1, x2. F3 means it is the pair triplets of the form x1, x2, x3, etc. Fn is x1, x2, x3, etc. xn. In general, we consider the space Fn. How we define the addition and scalar multiplication in Fn? Consider Fn, it is the set of all n tuples x1, x2, x3, etc. xn, where xi belongs to f for every I. This is Fn. If x is an element of Fn, then x is an n tuple x1, x2, x3, etc. xn. Okay. Its additive inverse is minus x. Is minus x1, minus x2, minus x3, etc. minus x. Okay. If y is any other element, say y equal to y1, y2, y3, etc. yn, then we define the addition of x and y as x plus y. It is an n tuple with corresponding entries as the sum of corresponding entries of x and y. So first entry is x1 plus y1, second entry is x2 plus y2, third entry is x3 plus y3, etc. Nth entry is xn plus y. This is the addition. Adding the corresponding or coordinates or entries of the given elements, we get x plus y. Similarly, we define the scalar multiplication as Cx equal to C, x is x1, x2, x3, etc. xn, that is Cx1, Cx2, Cx3, etc. Cx. This is the scalar multiplication. X is multiplied by C means every coordinate of x is multiplied by C, and consider it as an n tuple. This is addition. Okay. Now, if we consider the set of matrices, the additive identity is 0, which is the 0 matrix. In the set of matrices, additive identity means it is denoted by 0. 0 is the 0 matrix. And if A is any matrix, its additive inverse is minus A. Minus A is obtained from A by taking negatives of all entries of the matrix A. Similarly, if we consider the set of all functions f, then its additive inverse of the set is the 0 function. Denoted by 0, it is defined as 0 of x equal to x for every x. That is the image of any, 0 of x equal to 0. The image of any x is 0. It is called the 0 function, and additive identity of the set of functions is the 0 function. And the additive inverse of f is minus f. Okay, minus f is defined as minus f of x equal to minus of f of x. This is the additive inverse in the set of all functions. If we consider the set of all polynomials, then 0 additive identity 0 is the 0 polynomial, which is 0x raised to n plus 0x raised to n minus 1 plus etc. plus 0x plus 0. The 0 polynomial with all coefficients 0 is the 0 element of the set of all polynomials. Similarly, if p of x equal to an x raised to n plus an minus 1 x raised to n minus 1 plus etc. plus a1x plus a0 is a polynomial, then its inverse is minus of p of x, which is obtained by taking the negative of all coefficients of the given polynomial, which is minus an x raised to n minus an minus 1 x raised to n minus 1 minus etc. minus a1x minus a0. Okay. So we can, according to the given set or the proper nature of the given set, we can define the additive identity and additive inverse in the corresponding sets. Okay.